Hello everyone, welcome back to Physics 331. Today what I want to talk about is I want to finish our discussion of transmission line input impedance. So last time we calculated this expression where if we had a transmission line of length L terminated by a impedance ZL, we could calculate what the effective impedance looking into the transmission line was, and it was this somewhat complicated expression. So the first thing we're going to do is look at some special cases and see what Zn looks like for those special cases. And then in the second part of the video, what I'd like to do is to go over a little bit of a discussion of impedance matching, and then maybe prep you a little bit for assignment number 2. Okay, so let's start with some special cases. So special cases of Zn. So one case is that we set beta L, the wave number times L, equal to some integer multiple of pi. Okay, and so what physically does that actually represent? Well, beta is 2 pi over lambda, L equals to n pi, and so we can cancel the factors of pi. And if we solve for the length, what we find is that the length is an integer multiple of lambda by 2. So we set our transmission line to have a length that's equal to half a wavelength or one wavelength or 1.5 wavelengths of whatever the signal propagating in the transmission line is. Okay, so in this case, in our expression for Zn, we have to evaluate the tangent of beta L, and so the tan of beta L would go to, in this case, the tangent of n times pi. Tan is sine over cos, and the sine of an integer multiple of pi is 0, and the cosine of an integer multiple of pi is plus or minus 1, and so we have 0 over plus or minus 1, and so that's just 0. Okay, so in this case, the terms with the tangents in the numerator and denominator just go to 0, and we're left with Zn is equal to ZL. So in this case, Zn is going to be equal to Z0, and then, sorry, what was it? It was going to be ZL divided by Z0, and of course the Z0 cancels, and what we end up with is that Zn is just equal to the load impedance. And so the effect of the transmission line is just to transport that load impedance at its far end to look like it's just located right at the near end, at the input of the transmission line. Okay, so that's one case. A second case is we can choose to set beta L to be equal to, say, n prime times pi over 2, where we specify that n prime is odd. N prime we're not going to consider n prime being even, because then we're going to have beta L is going to be some multiple of pi, which is just case 1, which we considered already. Okay, so let's again think about what that means physically for the length of our transmission line. Beta is 2 pi over lambda, n prime times pi over 2. So let's see, the pi's cancel again, and if we solve for the length, what we get is L is equal to n prime times lambda, and then we're going to have a 4. So it's a odd multiple of 1/4 of a wavelength. So it's a quarter wavelength, 3/4 of a wavelength, 5/4 of a wavelength, and so on. Okay, in this case, if we look at tan beta L going to the tangent of, say, n prime lambda by 4, where remember n prime is odd. Oh, sorry. Sorry, I didn't want to do that. Let me fix this. I want to just go back to what we originally had, not in terms of lambda, but in terms of pi over 2, right? So, sorry, beta L is n prime times pi over 2. Okay, so tangent is sine over cos. Sine of pi over 2 is 1. Cos of pi over 2, or any odd multiple of that, is 0. And so we have 1 over 0. And in this case, tan beta L goes to, well, sorry, and so this is equal to infinity. In fact, I guess plus or minus infinity, because if we were at 3 pi over 2, the sign would be minus 1, so it would be plus or minus infinity. Okay, so what does that mean for Zn? Zn is equal to Z0, and then it's going to be ZL plus JZ0, so it's going to be ZL plus JZ0, and then we have plus or minus infinity for our tan, and then down here we have Z0 plus JZL plus or minus infinity. Okay, so this imaginary term is going to dominate the real term in both the numerator and the denominator, and so this is going to be Z0 over JZ0 plus or minus infinity over JZL plus or minus infinity. So the J's cancel. Oh. The J's cancel. The tan beta L's are the same infinities, and so they cancel. And what we end up with is Zn is going to go to Z0 squared over ZL for the case of L equals to n prime, an odd multiple of lambda by 4. Okay, good. So there's one more case, and this is perhaps the most important case, and that is the case where we set the load impedance to be equal to the characteristic impedance of the transmission line. So load impedance matches the characteristic impedance of the transmission line. Okay, so Zn is equal to Z0, and let's see, it's ZL plus JZ0 in the numerator. So it's ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. Well, what we're going to do is we're going to take the load impedance and set that to be Z0 in both the numerator and the denominator. And then the numerator and the denominator are exactly equal, so they just cancel completely, and we get Z0. And so that means Zn is equal to Z0 when ZL is set equal to Z0. And it doesn't matter what the length of the transmission line is this is true for all values of the transmission line length. Okay, good. And so we're going to see that that has some important practical implications. And so first, let's do a little bit of an aside here, and let's talk about impedance matching. And I'm going to start by talking about just regular circuits. Forget about transmission lines. Let's just think about simple circuits where we can ignore all transmission line effects. Okay, so impedance matching. So I want to think about a circuit that consists of a function generator, and so maybe this is some input voltage from your function generator, and then all function generators have some kind of output impedance. And so let's say that this is, we'll just think of this as a resistor, and so we'll call it RG. It's the output resistance of your function generator. Okay, and then so maybe we'll put this in like a little dashed box, and we could say that this is your function generator. So it has a voltage source. I'm thinking of this as like a sinusoidal function generator, and an output impedance, which we're going to consider as just a resistance RG. And then we're going to connect that to some external resistor, which acts as our load, and that's RL. And so what we could do is we could have we could measure the voltage VL across our load resistance. We could measure the current IL in our load resistance. So I want to think about the following. Well, actually, before we do that, let's just think about, say, calculating the current in our load resistance. So the current in RL. So it's just given by the output voltage divided by the total resistance in our circuit, which is a series combination of RG and RL. And so what we could do is we could say, well, what if I wanted to get the largest possible current in my load resistor? Well, looking at this expression, what we want to do is make the denominator as small as possible to get the largest possible current, and so that could be achieved by making RL as small as possible. So to get the maximum possible current IL, we would set RL to be as small as possible. We could make it as close to zero as we can. All right, so we could ask a different question. We could say, well, what if I wanted to get the maximum voltage across this RL? Okay, so this circuit, the voltage across RL is determined by a voltage divider, and this voltage is going to be given by whatever voltage the function generator is supplying, and then it's also multiplied by this ratio of resistors, RL divided by RG plus RL. Okay, so what do I need to do to make this VL as large as possible? This ratio in the brackets is always going to be a number less than 1 because it's RL divided by RL plus something. And so the best I could do is make that to be as close to 1 as possible. And the way I make that as close to 1 as possible is by making RL very large so that RL dominates RG in the denominator. And so to get the maximum possible voltage across our load resistor, we set RL to be as large as possible. So we make it as close to infinity as we can. And so there's these two extremes here where If I want a large current, I make RL small. If I want a large voltage, I make RL large. So sometimes really what you pay for is power. And so what you might want to do is you might want to say, well, what do I have to do to make the power delivered to RL as large as possible? How do we maximize the power delivered to RL? Okay, so the power is given by the product of the voltage and the current, VL times IL. We just calculated both of those things. So if I take my VL, which is Vn times RL divided by Rg plus RL, times IL, which is Vn divided by Rg plus RL, then this power is given by Vn squared, and then it's RL divided by Rg plus RL squared. So the idea here is our function generator is say a fixed piece of equipment. So we set Vn to be some value and it has some output impedance Rg. And so what we can actually adjust is RL. So we want to tune RL until PL is a maximum. So we know how to do that mathematically. We're going to take the derivative of PL with respect to RL and set that to be equal to 0. So we want the derivative of the power with respect to RL to be equal to 0. So this derivative is not too difficult to evaluate. We have to use product rule and maybe quotient rule. So the first term is going to be Vn squared divided by Rg plus RL squared. And then we're going to get a minus 2 from the derivative of the denominator. We'll have our Vn squared and our RL in the numerator. And then we have to lower the power of the denominator by 1. Okay, and so we want that equal to 0. So both terms have a Vn squared, so we can count those. Both terms have a 1 over RL squared, so we can get rid of that, and so the power becomes 1 in the second term. And so what we're left with, therefore, is 0 is equal to 1 minus 2 RL over Rg plus RL. And then we solve for RL, and that will tell us the value that maximizes the power. So let's see, what do we get? We get 2RL is equal to Rg plus RL. Subtract RL from both sides, and therefore we want RL to be equal to Rg. So what this shows us is that to maximize the power delivered to the load, we need to match its resistance to the output resistance of the function generator. So to get the max power transfer to the load, we need to match the value of RL to the output impedance or resistance Rg of the generator. Okay, and so this is called impedance matching. So of course, if you can, what you would do is you would just build this circuit, and if you want to maximize power, you would just choose your RL to be equal to Rg. But that's not always possible to do. So for example, maybe you have a certain device, your load, and that's a fixed device, and you can't modify it to change its RL value, its impedance. And so there are some strategies that people have come up with that you can use to adjust the effective impedance of your load so that it's matched to the output impedance of the generator. So one strategy for impedance matching is to use a transformer. Okay, so transformers are just two coils, a primary and a secondary, and they have a different number of turns. And so if you run a current through the primary, it induces a magnetic flux in the coil, and that magnetic flux is coupled to the secondary coil. And if it has a different number of windings, that changing magnetic flux, if it's an AC signal, will induce an EMF in the secondary. And if you adjust the ratio of the turns, you can make that induced EMF larger or smaller. Okay, so let's consider the following. Let's have our signal generator, V in, and then we have our output impedance of that generator, RG. So that's our function generator. Now what we're going to do is we're going to connect that to a transformer, and so symbolically the transformer has one set of windings. The number of turns in this windings is N1, and this is called the primary. And then there's a second set of windings, and it has maybe N2 turns, and that's known as the secondary. And then what we're going to do is connect our load resistance RL to the secondary. And so maybe this is a case where RL cannot be made directly equal to RG. So the question is, what should the ratio of turns N1 over N2, for example, be in order to achieve the desired impedance match? So I'm going to label a few things here. The voltage across our primary is going to be V1, and the current in our primary will be I1, and the voltage in our secondary will be V2, and the current in our secondary would be I2. What we would like to do is we'd like to consider this part of the circuit as some kind of composite component, and we want that component to have an impedance Z that's equal to RG. So we want the effective impedance of everything in the dashed box. Whoops. To be Z1. So if we look at this dashed box, what does it have? It has a current I1 going into it, and it has a voltage V1 across it. And so if we want to calculate its impedance, that's just going to be V1 divided by I1, and we want that to be equal to RG. Okay, so that's the goal, and so let's see if we can do a bit of analysis. I'm going to state some results which you may or may not be familiar with, depending on if you've studied transformers before. So, transformers can be used to step up or step down a voltage, and so the V2 on the secondary side of the transformer is equal to V1 times the ratio of turns N2 over N1. So if you wanted to step a voltage up, which sometimes you would, then you would make N2 bigger than N1. And so if it was double, you would get double the voltage. Sometimes often you actually want to step the voltage down. So what comes out of our walls, the sockets on our walls, is about 120 volts, and then you want to charge your phone with that, but your phone wants to be charged with 5 volts. So what your charger has in it is a little transformer to take the high voltage out of the wall and drop it down to a lower voltage. So you would make your N2 turns much less than N1 in order to step that voltage down. Yeah. In addition to that, you're going to charge your phone with a DC voltage and what AC is coming out of the wall. So you would also have some kind of circuit, a rectifier circuit, to turn the AC oscillating voltage into a DC constant voltage. Now, the current, you don't get that voltage change for free. The current is going to be stepped in the opposite sense. And so if you had a step up in voltage, you're going to step your current down. So that if you took the product of V2 times I2, it would be equal to V1 times I1, and the ratio of the turns would just cancel. So you don't gain any power. Okay, so let's not multiply them. Let's take their ratio. So let's then consider V2 over I2, which is going to be V1 N2 N1 divided by I1 N1 over N2, which is V1 over I1 times N2 over N1 squared. So if we go look at this circuit, if I take V2, that's the voltage across RL, and then I divide by I2, that's the current in RL. Well, this is just the resistance RL. So this would be, we might call that Z2, but that's just equal to RL. And then we said that the V1 over I1 at these terminals was the impedance that we wanted to calculate, Z1, and we want to ultimately set that to be equal to RG. And so this is going to be Z1, and we want that to be equal to RG. And so therefore, what we found is that RL is equal to RG times N2 over N1 squared, or maybe more conveniently, we could say that RG, let's see, is equal to RL N1 over N2 squared. And so that's the condition that would determine what ratio of turns that we wanted. So, for example, if RG was, say, 50 ohms, and RL was 200 ohms, so it was 4 times too big, then what we would want to do is set N1 over N2 to be 1/2, so that when we square it, we get 1/4, and the RL, which is 4 times too big, would be transformed down to be equal to the 50 ohms. And so we'd want twice the number of turns on the secondary as the primary. Okay, and so that's like an impedance matching method using a transformer. So impedance matching using, using a transformer. Okay, so the last thing I want to do is maybe set up assignment number 2, which is posted to the course website. And in this assignment, we're going to introduce another impedance matching technique using transmission lines. Okay, and so transmission line, it's called a tuning stub. Tuning stub impedance matching. So let's consider the following. Let's suppose that we have a long transmission line, and then one end is terminated with an impedance ZL. And let's say that in general that's connected to some kind of signal generator, maybe over here. Well, okay, let me just draw a signal generator. So maybe we have a signal generator that outputs voltage and has an output impedance of, say, Z naught. And we want to extract the maximum amount of power from this signal generator, but the problem is that ZL is not matched to Z naught. So the strategy is going to be to create a junction somewhere along this transmission line. And so maybe that junction occurs here, so that this length is perhaps X. And what we can do is we could calculate the impedance, let's say ZX, that occurs right here. ZX is going to be equal to the characteristic impedance of the transmission line times, well, that's something we started with here. So let's go all the way back. And so it's going to be ZL plus JZ0 times tan beta L. So ZL plus JZ0 tan beta. And so instead of the full length of the transmission line, now we're just thinking of a section of length L. And then it's going to be Z0 plus J ZL tan beta X, where we're assuming that the characteristic impedance of the line is the Z0, the same as the output impedance of the function generator. And so that's still not going to be matched to Z0. So what we're going to do then is, in the next step, we'll take that same junction, and so we still have this section of length X, and it's terminated by an impedance ZL, and we're going to connect another parallel transmission line, and we can attach whatever we want to it, but maybe we leave a short circuit. So that for this transmission line, it's terminated by a load impedance of ZL equals 0. And we can pick the length of this thing, and maybe we pick its length to be Y. And so we can write down a impedance for this section of transmission line of length Y. It's going to be ZY is going to be Z0. Now, ZL is equal to 0. So we get 0 plus J Z0 tan beta Y. And then we have divided by Z0 plus 0. Okay. And then what we can do is we can say, well, the net impedance at this junction is the parallel combination of these two. It's the parallel combination of ZX and ZL, right? So Z net at the junction is the parallel impedance of ZX and ZY. And that's going to be a complex number. It's going to have real and imaginary parts. But what we have are two parameters to tune. We can tune the length X where we place this junction, and we can tune the length Y of the so-called stub that we place at that junction. And it turns out with those two parameters, we can balance the real and imaginary parts until they're equal to, I forgot to write my output impedance here, Z0. So if Z0 is real, say it's 50 ohms, we're going to adjust X and Y until the imaginary part of Z net is equal to 0, and until the real part is equal to the desired 50 ohms. And that's what you're going to work on in assignment 2. It's part of assignment 2. And so there's a few steps that will try to walk you through that problem. Okay, good. That's where I want to stop. Thank you very much, and we'll talk next time.